So for the absolute value function, go ahead, take your first door. I don't really care which order that you're going to do it in. I'm going to do it in this order. So the absolute value is going to be my top left-hand door. So on the door, I'm going to put a few things. So the title or the name of it, so I know it's absolute value. What the equation looks like for the parent function. And then we want to graph the parent function of absolute value, and next to that graph we'll write the domain and the range. Okay? So just kind of all on the front. So what does the absolute value graph look like? So a little bit of review for your quiz tomorrow, right? Okay, it looks like a V. Okay? And for the parent function, where was the vertex of the V? 0, 0. And for the parent function, did it face up or down? Up. And what were the slopes of the sides? 1. Okay? And absolute value is the only one that has a real slope of its side because the sides are lines and not curves. So you're going to have a point at 0, 0. And then go ahead just to emphasize that the slope is 1. Give yourself that point at 1, 1 and at negative 1, 1. And then go ahead and draw your V. Okay. So the domain and the range. If you don't know that D and R mean domain and range, write the whole words out on your paper. Yeah, this is just all still on the outside. Okay? But this is the last thing. It'll go right, and it can go in this part of the graph. It doesn't matter. All right, so domain. What is the domain of the absolute value function? All real numbers, because we can move anywhere to the left and right, still plug in those x values and get something on the graph. So the domain is all real numbers. Okay. What is the range of the parent function for the absolute value graph? Good. So range is looking up and down. Does the graph ever reach a maximum, minimum, or have a hole? So it goes forever up, so we don't have to worry about that stuff. But this is the lowest point. So like Stephen said, everything is going to be at or above 0 for the y values. So we would say that y is greater than or equal to 0. All right, and then I know I said our concentration is going to be learning all the parent functions, which it is. But since your quiz tomorrow is on graphing absolute value functions and graphing greatest integer functions, why don't we put the examples into your organizer now so you get a little refresher for your quiz tomorrow? Does that sound okay? All right. So go ahead and open the absolute value door. So on one side, you kind of have two spots behind the door, right? And I don't care which is which. But on one side, we're going to write an equation. We're going to graph what that equation looks like with some different transformations and write the domain and range. And on the other side, we're going to list out all the transformations so we can get used to doing that. Okay? So here's the equation I'm going to have you write in one section. So y equals negative 1/2 times the absolute value of x plus 3 and then minus 1. It doesn't matter which side, but just one side we'll put the equation in the graph that goes with it, and on the other side we'll write out the transformations. Okay. So on the same side that you put this equation, we're going to put a graph of what this looks like. Now, with the absolute value function, I would expect you to still be able to list the transformations, but we don't depend as much on the transformations to graph it like we did with the step functions. We kind of found a shortcut for the absolute value functions that works really quickly, but we don't need to know all of the transformations. Okay? So what information did we want to pick out of the absolute value function to be able to graph it? What's the first point you want to put on the graph? The vertex, right? And we get the vertex from which parts of the equation? The h and k. And what's the h value in this case? Negative 3, right? All the inside horizontal stuff is wacky. So negative 3, and the k value is negative 1. So our vertex is going to be at negative 3, negative 1. All right, so then should our V go upward or downward? Down, because the A value is negative. And again, because the absolute value has straight sides, this is why it's almost easier to just do it this way instead of with the transformations. We can just use this A value as the slope. So I'm going to make sure my V faces downward, and I'm going to use a slope where it's 1 is the rise and 2 is the run. Okay? So since I want it to go downward, I'm going to go down 1 over 2. And then I'm going to go down 1 over 2 the other direction as well, so that I have this V. Okay. Is everybody okay with remembering how to graph the absolute value function? So there will be a couple of those on your quiz tomorrow, 2 problems for you to graph absolute value. Okay? That should be how you do it. Pick out your A, H, and K. What we're going to do in the other section that you have there is we're just going to list all of the transformations. So again, we don't use them as much in absolute value, but we have to be really good at identifying them anyways. So we're just going to get used to it and list what the transformations are next to it. So the other section is going to be to list transformations. All right, so the transformations are all the changes that took place from the parent function. Different types of translations, vertical or horizontal, so left, right, up, down, how many units, stretches and compressions, whether they're vertical, horizontal, and what you multiplied by, or reflections, and whether they were horizontal or vertical. So let's start with just listing all the horizontal stuff. Again, I told you guys I would be really consistent in class that I would always list like horizontal stuff, then vertical stuff, so people get used to where they are. So where do we look for horizontal transformations at? Inside the function, right? So how many transformations are there? 1. Okay, and what kind of transformation is this? To the left 3. Okay, so we would list one of the things as being the fact that we go to the left 3 units. Okay? That would be our only horizontal change. Okay? Everything else that changed about this graph was vertical because nothing else is happening on the inside. How many vertical transformations are there? So this is one of them. The number 1/2 is one of them. And the negative is a separate one. Okay? Now, when we list our transformations in the horizontal category and in the vertical category, I told you guys I'm going to list reflections first so that when we are using them, I do that first so I don't accidentally move something, then reflect it, and end up in the wrong place. So we do have a vertical reflection because of the negative, so just for consistency while we're in here, I'm going to list that first. And everything we're listing here, even though we didn't use it to plot this graph, you should still see that it took place. You can see from the parent function that the whole graph shifted left 3. You can see that it faces downward instead of upward, so that's the vertical reflection. What is the 1/2 going to cause? It's vertical, and then we have to decide whether it's a stretch or compression. So remember with the vertical stuff, you get to use the number exactly like it is. So basically, we're going to take things and multiply it by 1/2. When you take values and you multiply them by 1/2, do distances get smaller or larger? Smaller, which would mean they're getting compressed. Okay, so if you can figure out the number first, you'll know which word to write here, whether it's horizontal or vertical. Okay, so this is going to be a vertical compression. Okay. And again, you could see that. Notice from our parent function, if we wanted the V to be the same shape as this one, we would have to take it and compress it vertically so that the sides were forced to go out wider. All right, and then what about the -1 that's at the end of the equation? Down 1. Okay. All right. So I'll ask you to graph the absolute value function. It'll be some equation like that. I'll ask you to list the transformations, but you don't really have to use them to get the graph. The other thing I'll ask you again is the domain and the range. Okay? So looking back to your graph, and again, you can just write it in a quadrant of the graph or next to it, wherever you have the most space. The domain and range are not always going to be exactly the same as the parent function. Sometimes they will, sometimes they won't. What's the domain of this absolute value graph going to be? All real numbers, okay? Because your V still goes forever left and right, no gaps, so any x value you pick will have a point that you could find on the graph that goes with it. So all real numbers for domain. So basically for absolute value functions, the domain is always going to be all real numbers, right? Because there's always going to be a v that goes forever outward, okay, left and right, whether they face up or face down. It's the range that's going to change and kind of be dictated by which way the v faces and where the vertex is. So for our range in this case, talking about y values, are the y values all below a certain point or are they all above a certain point? Below, right? So they're all below. All our points in our graph, our y values on our graph are below this point. So y is less than or equal to. And what was the height of this point? -1. So that would be my range. Okay. All right, any questions on how we graph absolute values, why we listed any of the transformations that we did, or how we got domain and range? Okay, so let's fill in the other parent. The next parent function we're going to do is the greatest integer function, and that's on your quiz too, so we'll do that example together too before we fill in the other parents, so you guys have a little bit of practice with that again before your quiz tomorrow, okay? All right, so the next function is the greatest integer function. So the parent function for that uses the brackets. What did this graph look like? Steps, okay? And then there were some characteristics about the steps you want to know for the parent function. So where does the main step start? Where is that like vertex point? I kind of use that. No mathematician would call it a vertex point, but we'll just keep calling that special point on every graph our vertex point, okay? 0, 0 still. And then there are some things I should know about the steps, like how long they are and how far apart they are. So what are those characteristics? How long is each step? 1 unit long. And the distance from that step to the next one? 1 unit apart. Okay, so that's all true for the parent function. So the parent function is going to have a step that goes like this, and then jumps up 1, this, jumps up 1, this. And the steps go forever in both directions. Okay? What is the domain of the greatest integer function? Still all real numbers. You can plug any number you want into here. You have to figure out how to round it properly, but you'll always get an answer. So the domain is still all real numbers. And the range for this one was kind of weird. Yeah, we used the z to represent it. What did the z stand for? All integers, because what it did is instead of hitting the numbers in between, it only hit like -2, -1, 0, 1, 2, 3. So those type of numbers are called integers. So you can write the z. If you don't like the z, you can totally write all integers if that makes more sense to you. Okay? All right, now what we're going to do is we'll go through an example. You guys don't have a lot of space, and I think it's harder to graph the greatest integer function than the absolute value function. So we'll do it together up here, and then you guys can write the product down so that you have the answer to the example. You could go home and then try it yourself separately and see if you get the same answer. But we'll go through all the changes up here and see if you guys can do them. If you want to go through all the changes with us, just grab a sheet of scratch paper and do an extra example of the greatest integer function if you wanted tonight to study. Okay? So the equation I'm going to give you guys is going to be 2 negative x plus 1 minus 3. Okay, so 2 times the greatest integer function, and inside the function there's a negative x plus 1, and then a minus 3. So the first thing I want to point out to you guys is that the horizontal stuff is not written in the best form. Why is it not okay the way that it's written right now? Yeah, because there's some coefficient in front of x other than just positive 1. So whether this is just a negative or it's a negative and a number or just a number, we want to rewrite that with that part factored out. Not out of the greatest integer function, but just so that it's separated from the other stuff inside of there. Otherwise, you won't be seeing the right h values, okay? So when we factor a negative out of this, we're going to have x, and what's the second term that we're going to have? Minus 1 instead of plus. All right, and we'll go through a bunch of stuff before we come back and do the graph, but we can go ahead and list the transformations because we're going to use the transformations to help us graph. So let's make that list, and then up here, I'll go through all of those steps separately, and then we can all write the final product in the organizer, okay? And it'll be good review for your quiz tomorrow. So transformations. So again, let's start with listing all the horizontal stuff. If there's a reflection in that category, we'll put that at the top of the list, and then we'll list the rest of it. So what's the first transformation I should list? Okay, good. So I heard two different things. They're both right. I'm going to list the reflection first just so I don't mess up any of the shifting with the reflection. So because this negative is in here, that's a horizontal reflection. You guys can abbreviate the same things I abbreviate on your test. If I can tell what you're saying, I'm good. Okay. And then I heard that because it said x minus 1, that meant we were going to shift to the right one. Okay. All right, now let's go ahead and list all the vertical stuff that's happening. So I heard 3. Is everybody good with that? Because of that minus 3 that's over here at the end. So we're going to go down 3. Good. Okay, and so this right here, right, we see the times 2. So immediately it should be like, okay, a number multiplying is a stretch or compression. In the vertical world, I just kind of get to keep the number the same. So if you have to, write that part down first. Times 2. When you multiply stuff by 2, do the distances get bigger or smaller? Bigger. So then I'm going to call it a stretch, because that would mean things are getting bigger in that direction. Okay. So if I can decide the number, I can usually decide the label that goes with it. All right. Okay. So let's go ahead and do these things. All right. So I'm going to use my parent graph to start, but you guys obviously aren't going to write on your parent graph because you want just the plain parent graph. But I'm just going to do the first transformation on here, copy and paste this to another page so we can go through all of them, and then put the final answer right here that you guys can copy into your organizer. Okay? So here's the parent function. Okay? I don't always start with all these steps on the parent function, but because of the stretches and compressions, you do need more than just one step. Or if we like change the distances between them, you're not going to see those things. So I like to keep like 3 steps. The main one, okay, that has that vertex point, and then a couple around it so I can see the reflections and any sort of stretches and compressions that happen. Okay, so the first thing that happens is I'm going to do a horizontal reflection. So how do I do that? What changes to where when we do a horizontal reflection? So basically you have to decide, are you flipping stuff over the x-axis to do a horizontal reflection, or are you flipping stuff over the y-axis? The y-axis, because if stuff is flipping over the y-axis, it's going to go from the right side to the left side and from the left side to the right side, which that would be a horizontal change. Okay? So that means everything that's on that axis is going to stay, so this point's going to stay here. But instead of the step going to the right and having this point at 1, 0, it's going to go to the left, and it's going to have that point at negative 1, 0. Okay, so this has been reflected over here. Same idea here. This step is going to get reflected to this side. So it's going to look like this. And this step that was here is going to get reflected to this side. So this point is going to be here. It's going to go this way. All right, is that okay with everybody? So here's this line I used for reflection. Everything got flipped to from one side to the other. Okay? If it was 5 spaces away over here, I would have made it 5 spaces away over here, all horizontally. Okay? All right. The next thing we're going to do is we're going to move everything to the right one. So I'm going to go ahead and take the steps that I have and just move them all one space to the right. Okay. So this main step right here, kind of don't want to lose track of the fact that's my main one. Now I'm going to go right here. Okay. This step is going to end up here. And this step is going to end up here. Okay. Any questions on the horizontal reflection or moving to the right one? So you feel like if you wrote those things out and you had the parent function on your quiz tomorrow, you could do the horizontal reflection and then you can move it to the right. All right, so then we're going to move everything down 3. So again, this is kind of my main step. We start with that one. So it's going to be here. So the ones around it will also go down 3. So all these steps got moved down 3 so that they're now right here. Okay? Any question on moving down 3? Now, my main step is still this guy in the middle. That's important to know because whenever you stretch or compress anything, that is the step that's going to be stretched or compressed, okay, towards or away from. But the vertex point is not going to change. So that's what you want to pay attention to. So I'm going to erase some stuff and then do the last step. Can't decide if this was the... Okay. So we have everything here, and the last thing we do is we want to vertically stretch it by 2. What is that going to change about our step picture? Like just in general, what about the picture is going to change if you're vertically stretching it by a factor of 2? Okay, so Stephen's going like this, all right? So is the length of your step going to change? The fact that the step is 1 unit long horizontally, is that going to change? No, okay? The fact that the steps are 1 unit apart vertically, is that going to change? Yes, okay? But if you don't have a starting point, like, oh, keep this one here and then stretch everything away from it, how do you know which ones to move which direction? I could move these a lot of places to make them 2 units apart. But how do I know which one's the right one? The right choice is to keep the step that has the vertex on it in the same place. So this step right here is not going to change. Things are going to be stretched towards or away from that step that has the vertex point in it. Okay, so that vertex is really important. It's not going to move with stretches and compressions. Okay? So this step right here below it, what's the current vertical distance between this vertex point and this step below it? 1 unit. Okay? So it was 1 unit. My stretch says to multiply by 2. It means when I draw my final graph, I want that step to be 2 units away from the vertex point. Okay? In the same direction it was. If it was below my vertex point, I want it to stay below my vertex point. I would just like it to be a total of 2 units. Now, that doesn't mean 2 units from where it is right now. It just means redraw this step so that it's still below this one, but rather than having a distance of 1 between them, the vertical distance now needs to be 2. Okay? So this is going to be here. Okay. This step is not changing. Okay. So this step is now not part of my graph. Do we understand that? Okay, it was there. I just repositioned it so that the total vertical distance between steps now is 2. I'm going to do the same thing with this step. So this step was above, okay, the step that has the vertex point by 1 unit. Again, 1 times 2 is still going to be 2, so I still want them to be 2 places apart without moving this one. So I need this one to stay above it, but I want it to be 2 spaces above it instead of 1 space above it. And again, that does not mean move it 2 more places from where it is right now. It just means reposition it so that when you measure between the main step and the step that you have, they're 2 units apart. So this is going to move so that it's right here. Okay. And that means this is no longer part of our graph. Okay. So the main step stayed where it was. The steps that surround it were not moved anything left or right. They were just moved away from it so that their total distance was this new distance. Alexis? This one? -1. Is that okay? Okay? So this is your final graph that you guys would want to draw. Okay? So I would draw at least these 3 steps. And then if there's more space on my graph, I can continue the pattern that I now see. So I now see a pattern of which direction the steps are kind of going. And I know they're supposed to be 2 units apart. So if I was going to continue and add more steps to this graph, I know that after this one, 2 units above it, there would be another step that looks like that. Okay. Any questions about this? So again, start with your parent function. So you really need to make sure you know your step function parent. Okay. And then do the transformations that you list out. All right, what about the domain and range of this new graph? So this graph should now go in your organizer. This is the final graph of what that is. So I changed it, okay? I just wrote right on here, took my parent function, changed it. This is now the final graph of what you see there. And notice the vertex point, if you guys want kind of a quick checking thing to see if you did it right. You know how the h and the k in the absolute value function were the vertex? That should stay the same for every function. So like your h here is 1 and your k is -3. Your main vertex point should be at 1, -3, even when you're done with all the transformations. So you see 1, -3. That's where our main vertex point was. That tells me I probably did a pretty good job. I don't think I messed things up because I think things landed in the right spot. Okay? So just like how h and k in absolute value tell you the vertex, they give you an idea of where your vertex should end up here also, but there are some other things involved, okay? All right, so draw this graph inside so that you have the right picture. And then the question is, how would you list the domain and the range? So what's the domain of the function? Still all real numbers. So absolute value and step function both have all real numbers as their domain consistently. So there's a constant if you're kind of looking for something constant to grasp onto. Okay. All right, what about the range of this function? Just describe it to me as best as you can. What's that? Okay, so Stephen is saying all odd integers. So let's follow and see if what he seems to say is correct. So this step is sitting at a height of 1. There's no step at 0, then there's one at -1. There's no step at -2, then there's one at -3. There's no step at -4, there's one at -5. Is what Stephen said seem to be true? All the odd integers. So I would guess the next step would be at -7 and then at -9. As I went upward, this one was at 1, the next one would be 3, and the next one would be at 5. So that would be a fine way to say this. This could say odd integers. If you have trouble coming up with what the answer to that is, just express it however you can. If it's like a list with ... dots at the beginning and end because it's never ending and you know there's a pattern but you can't describe it in words, just try to tell me what it is, okay, however you can. All right, any questions about any of this stuff? No? All right, so you know what to expect on your quiz tomorrow, right? Okay. I would say anywhere from 2 to 4 graphing questions, but all of the graphs will either be absolute values or greatest integer functions. Okay? All right, so let's just fill in the rest of the parent functions. We're not going to do any more examples or listing transformations, just the rest of the front of the doors. Okay, so 4 more things, which is going to be your homework tonight. Practice the absolute value parent, practice the greatest integer function parent, and these other 4, because then you're going to use some of those in class after your quiz. All right, so one of them is a quadratic. So I did my quadratic below the absolute value. Again, I'm not really concerned about where your doors are, but I know some of you care about where I put them because you want them to be the same. Okay, this function would be y equals x squared. All right, so what do you guys know from Algebra 2 about this graph, y equals x squared? What kind of shape is it? What's that? Yeah, so it looks like a U. Anybody know what the technical name we gave the U is? Parabola. Okay. So the parent one is concave up. Again, its vertex is at 0, 0. And then it has a point at 1, 1 and negative 1, 1, kind of like absolute value. But it doesn't go out in a straight line, right? It curves up. That's because what happens when you plug 2 into this function? So you plug in 2 for x. 2 squared would equal 4. So your next point wouldn't be like up 1 over 1 again. When you go over 2, you actually go up 4 spaces. And then I'll mimic that on the other side also. So that's how you kind of get this curving feature. So when we graph parabolas, we're going to use transformations also. You can't do it like absolute value, even though they have a lot in common, because the absolute value has straight line sides. So you're like, oh, I go up this, over this, up this, over this. But this one, you go over 1, you go up 1. But when you go over 2, you go up 4. So when you graph this tonight, all I literally want you to do is be able to graph these 5 points. I'm just trying to help you memorize what this function looks like for when we use it later. Okay? What would the domain of the function be? Here, do this. Take a minute in your groups and see if you guys can figure out the domain and the range of the function. You guys figure out for domain and range. What's domain? All real numbers. Okay. And what about the range? Okay, so again, just like the absolute value function, y is greater than or equal to 0. All right, the function that I put next to the quadratic function is the square root function. I put them next to each other because they have something in common. One's a square, one's a square root. They kind of undo each other. Now, the square root is a little more complicated. What numbers do you not want to plug underneath the radical if you're trying to plot points on this graph? Negative numbers, right? So that means 2 things. That kind of gives you a hint to what our domain is going to be, and it kind of tells you that our graph isn't really going to have any points over there in like the world where we would plug in negative x values. So I'm going to start by plugging in 0 because I don't really expect to plug in any negative values. I know imaginary numbers, I know all that stuff, but on this graph, these are all real numbers. So if I plug in a negative, I'm not going to be able to represent that on the graph. So I would start by plugging in 0. So again, the vertex point for this function would still be at 0, 0. Now, it's not going to be a vertex like a quadratic and an absolute value where it turns around at that point. But by vertex here, I mean like our main point in the function when we stretch and compress stuff. It always goes like towards that point or away from that point. Okay? All right, and then we're going to have 1, 1, because when you plug in 1, the square root of 1 is 1. What's another nice number to plug in so you can calculate its square root? 4. So when we plug in 4, we would get a square root of 2. So our graph goes something like this. It does continue to grow upward. It's just really slow. Because think about it. What would be the next nice number to plug into the square root after 4? 9. And at 9, you would reach 3. And then it would take you all the way to 16 just to get up to 4. So, like, could you eventually reach 10? Yeah. But you're not going to reach a height of 10 until you plug in the number 100. So it's growing. It just grows very slowly. Okay? So what is the domain of this function? Which x values are okay for us to plug in? Positive values and 0, right? So basically everything from here over. okay? But we couldn't plug in any x stuff over here. And you can see that on the graph. Do any of these x values correspond to a point on the graph? No. Only starting here do we get points on the graph for every x value out this way. So x has to be greater than or equal to 0. And what about the y values for this graph? What about the range? So the graph has an endpoint here, and then it continues to grow upward just very slowly. Good. So again, it will go forever upward, just at a slow pace. But this is kind of the minimum point it hits, and it doesn't go below that. So all the y values would also be greater than or equal to 0. Okay. Now, just a quick side note. You guys don't have to write any of this down. An example of something that then went through and changed So all the work you did with transformations, if you learned them well while we're working with the greatest integer function, you're just going to be able to take that knowledge and apply it to this. So you don't have to write this down. I'm just trying to demonstrate for you how this is going to work. So what's the horizontal transformation that's happening in this function? So inside the radical, what's the only thing that's affecting the function? What number is it? 2. It's multiplying it. So is it a translation, a reflection, or a stretch or compression? Stretch or compression, right? Something in that category? Okay. So remember with the horizontal stuff, it's wacky, right? So you have to use the reciprocal. So if we times stuff by 1/2, would you call that a horizontal stretch or a horizontal compression? Compression. Okay. Again, you're not writing any of this down. I'm just demonstrating for you how the same stuff you know, we're just going to use over and over again. So that means if I wanted to do a horizontal compression in this graph, vertex point stays. Okay. All the horizontal distances from the points are going to get compressed towards the vertex point. So like this point right here. How far is it from the vertex point only horizontally? 1 over, right? What's 1 times 1/2? 1/2? I'm going to relocate this point so it's only half a unit away from the point instead of 1 unit over. Okay? This point over here, how far is it horizontally from the vertex point? 4. What's 4 times 1/2? 2. I would move that point so it's only 2 units away. Oops, sorry. And I would get a graph like this where it's getting horizontally compressed backwards. Okay? What transformation does that cause, the negative that's out in front? Reflection. Vertical or horizontal reflection? Is it inside the function or outside the function? Outside. So is it vertical or horizontal? Vertical. Okay? Vertical means you go from up to down, which means you flip over this line. So this guy would stay. This guy would get flipped over here. And this guy would get flipped over here. Okay? So the red got flipped over so that it looks like the green. Okay? What's the last transformation that would take place in this graph that I haven't done? Up 1. Okay? So the very last thing I would do is I would move this whole graph up 1. So the vertex point would get moved here. This point would get moved here. And this point would get moved here. So my point in showing you this is you just learned what a square root graph looks like. But if you had the parent memorized, could you do the same exact stuff that we've done with every other function? Yes. So the point in learning the transformations is that then you don't have to learn how to graph 6 different things. You have to know 6 different starting graphs, but if you know how to do the transformations, you know how to change all of them. They're all changed the same way. Okay? So we'll do more examples of that, but the worksheet that you get tomorrow is going to have all the different functions on it after your quiz. Your quiz is just on absolute value and greatest integer. I wouldn't surprise you with something we did today. That wouldn't be fair. But after your quiz, the worksheet that you're going to get is going to have, simpler than this, no horizontal stretches, compressions, or reflections. But it's going to have problems like this where it has a lot of shifting, maybe a vertical reflection of all the different shapes and you're going to try to use the parent graphs that we put on there and change them like this to do it. Does that make sense to you what my expectation is afterwards? I don't expect you to be perfect, but it's the same changes we've always done, just with these new starting places. Okay? Mm-hmm. You don't get to use this on the quiz. Okay? The quiz is only about the absolute value and the greatest integer, so you'll want to practice those and make sure those two are for sure down perfect tonight. When you do the tomorrow night's homework and you're doing the graphs of all different, I would totally expect you to rely on the stuff we write in it today to do that. Okay? All right. The last two you guys have to put in there is a cubic and a cube root. So a cubic function is when the x is cubed instead of when it's squared. Does anybody remember this from Algebra 2? Got a couple people. All right. So basically, we'll plug in a couple points so you can get the idea, and then I'll show you how it looks. So when you plug 0 in here, what do you get? 0. 0, 0 is again the vertex point. Okay? And then we just want a couple of points surrounding 0, 0. So what do you get when you plug 1 in here? 1. So it has the point 1, 1. What about when you plug negative 1 in and you cube it? You get negative 1. So a little different than a quadratic. The quadratic, both sides go up around the vertex, because when you square negatives, you get positives, and when you square positives, you get positives. But in a cubic, when you cube a negative, it stays negative. What about if you plugged in 2? You'd get 8. It would be way up there, right? So basically what's happening here is the graph is shooting way up. And then if I plugged in negative 2, negative 8, so this part side of the graph around the vertex shoots way down. So that's what a cubic looks like. It's going outwards, but it goes up really fast. So it almost looks vertical, but it's not. It's still going outwards. Okay? So what would be the domain of this function? All real numbers again. And what about the range? All real numbers, right? This time no maximum, no minimum, no stopping point. It just keeps climbing in both directions with no gaps. So it would be all real numbers also. And then the last parent function that you have to put on there is the cube root. So again, we'll plug in a couple points to see what this looks like. So when you plug in 0 and you take the cube root of that, what do you get? 0. So again, 0, 0 is your vertex point. I'm going to make that my first point right there. Okay, what about when you plug in 1? 1. The cube root of 1 is still 1. What about negative 1? Can you take the cube root of a negative? No. Is there a number that if you raise it to the third power, you'll get a negative answer? Yes. Then you can take the cube root of a negative and get back that negative answer. So the cube root of negative 1 is just negative 1. So we get these points. What would be another nice number that you could take the cube root of? 8. Yeah, okay, because then 2 times 2 times 2 would equal 8. So you'd have to go all the way out to 8 in order to get 2. And you'd have to go all the way out to negative 8 in order to get negative 2. So basically, something like this. Okay. So they're similar, right? But this one grows really fast. You plug a number in and it shoots up in value. This one grows really slow. So maybe that will help you remember which one has ends going which direction. What about domain and range for this graph? Yeah, again, both all real numbers because no gaps, no minimums or maximums in either direction. Okay? All right, so your homework tonight, just to copy down these 6 graphs on a separate sheet of paper. I know that seems stupid, but what I'm trying to get you to do is to memorize where the points are on the graph. Because as you saw, you know the transformations. If you can memorize these 6 graphs, all we have to do over the next week and a half or 2 weeks is practice. Before then, we figure out to assess how we're doing here, okay? So tomorrow, 2 to 4 questions, only absolute value and greatest integer function. So after you draw all your parent function graphs, if you want to look at what to review, go back to the sheet that you have on absolute value and the sheet you have on greatest integer and look at those graphs, okay?